All right, so our next talk is by Dan Moriarty on the South Pole Aitken Compositional Anomaly.
All right, thank you. So today I'm going to be talking about several different compositional anomalies within the South Pole Aitken Basin. So I'm sure most people in the room are pretty familiar with SPA, but just in case you're not, it's the largest and oldest confirmed impact basin on the surface of the moon. And given its extreme size, it's modeled to have excavated and melted significant volumes of lower crust and upper mantle materials. So the science themes for my talk today, I've been using M-cubed mineralogical data, and I've used that to identify 4 distinct compositional zones across the basin. So these zones have implications for using SPA as a probe to the lunar interior, as well as understanding its thermal and magmatic evolution. We're also going to touch on a new possible origin model for the SPA thorium hotspots that Ryan introduced earlier this morning. So our methods are grounded in M-cubed spectroscopy. So most mineralogical diversity across the surface of the moon can be described by differences in the abundance and composition of pyroxenes. This kind of difference in pyroxene abundance and composition is really easy to look at with M-cubed spectra. So what we do is we fit a 2-part linear continuum to each M-cubed spectrum. And then from there, that allows us to measure these diagnostic properties of the absorption bands. So we're looking at absorption band depth. That corresponds to pyroxene abundance. We're also looking at band center, and that corresponds to pyroxene composition. So in general, short wavelength absorption bands correspond to magnesium-rich pyroxenes, neritic materials. Longer wavelength absorption bands correspond to more iron and calcium-rich pyroxenes. So these are things like Mare basalts. So what we do is we calculate these parameters, and then we look at maps of these parameters to look at the distribution of different compositions across the lunar surface. So this is a map of the 2-micron band depth across SPA. Again, this is measuring pyroxene abundance. And so what this shows is that SPA breaks down into 3 basic zones based on pyroxene abundance. So there's this central pyroxene-bearing zone, which exhibits a pervasive elevated pyroxene abundance. There's the heterogeneous annulus outside of that, which is a little more mixed up. And then there's the SPA exterior, which is mostly feldspathic. So when we fold in pyroxene composition, we see that this central pyroxene-bearing zone breaks down into kind of 2 further regions based on composition. So in the center, we have the SPA compositional anomaly, or SPACA, and outside of that is the magnesium pyroxene annulus. So we've done a survey of large impact craters throughout SPA, looking at the kind of dominant compositions in the crater structures to establish a general stratigraphy for these different regions. I'm not going to talk much about the magnesium pyroxene annulus or the heterogeneous annulus today, but we did have a paper come out in JGR earlier in the year that pretty thoroughly describes those. The basic takeaway from looking at these regions is that the magnesium pyroxene annulus is this kind of vast region over 1,000 kilometers across, which exhibits a fairly uniform and very vertically thick deposit of magnesium pyroxene-bearing material. So based on some of these crater scalings, this material extends of depths of 40 to 50 kilometers or greater beneath the surface of SPA. So it's pretty clear that these magnesium pyroxene-bearing neritic materials were the primary materials that were kind of excavated and melted by the SPA forming impact. When we look at SPACA in the middle of SPA, we see that the surface materials have a much different composition. So when we look at the spectra over on the left, and then the pyroxene compositions as told by the 1 and 2 micron band centers on the right, we see that the SPACA materials, which are shown in green, they're intermediate to the magnesium pyroxene neritic materials in blue, and then your kind of typical Mare basalts shown in red. So the SPACA materials are intermediate in terms of both the overall albedo as well as the pyroxene composition. So where do these kind of unique materials come from? So for some insight into that, let's start looking at the physical properties of SPACA. So first, we're going to focus on an impact crater that's kind of in the center of SPACA here. This is Baba crater. When we look at a map of the M-cubed 2-micron absorption band center, again showing pyroxene compositions, I would like to say that this map is from a global mosaic of M-cubed data. So this is 10 times lower spatial resolution than individual M-cubed strips. But even at this lower resolution, we can see there are distinct compositional differences between the walls and rim of Baba versus the central peak. So the wall and rim are excavating material from the top 5 kilometers, and that all looks kind of similar to the Spaka surface material. And then the central peak, which originates from depths greater than 5 kilometers, that's exhibiting these magnesium pyroxene-bearing neritic materials. So at Baba, this suggests a kind of 2-layer stratigraphy, where we have about 5 kilometers of Spaka surface materials underlain by the more typical magnesium pyroxene-bearing materials. Baba is not the only location within Spaka where we see evidence for the stratigraphy. We also see some evidence for this at several other craters, including Finson and Stony. So this 2-layer stratigraphy appears to be kind of a pervasive feature of Spaka itself. So what's the source of this 2-layer stratigraphy? We can start to get an idea by looking at topography. So this is a topographic map from Lola across the Spaka region. You can see that the area looks fairly smooth in topography. And there's some hint that there may be a lower density of impact craters throughout this terrain. When we look at the catalog of Lola craters greater than 20 kilometers, we find that that's borne out. There is indeed a lower density of impact craters throughout this area. You'll notice that I've highlighted a number of craters in cyan across Spaka. These represent craters that have been significantly modified, either by burial, embayment, or flooding. So Spaka exhibits an overall low crater density, and then the craters that are there are all significantly modified. So this really speaks to a resurfacing origin for the nature of Spaka. So what's the nature of this resurfacing? For some insight into this, we can look at another feature within Spaka that's pointed out here. This is Mafic Mound. Mafic Mound is a local topographic high. In a 2015 paper, we investigated the morphology, topography, and composition of Mafic Mound, and we found that it was pretty similar to some volcanic complexes that we see elsewhere on the moon. So here I'm showing topographic profiles of Mafic Mound, and we're comparing that to several other volcanic complexes. So we're looking at Gardner, Mons Rumker, and Compton-Velkovich. Mafic Mound looks a heck of a lot like these volcanic complexes, so we interpret it to be a volcanic feature that formed in the center of SPA. So Mafic Mound is also the exact same composition as the rest of the Spaka material. And so for that reason, we're interpreting Spaka to have formed through volcanic resurfacing of the central portion of SPA by this kind of interesting, unique volcanic composition, a different magma than you see in your typical Mare basalts. So what's the nature of this magma? So for some insight into that, we've been looking at the lunar prospector thorium maps of SPA. And you can see that Spaka is associated with a local minimum in the thorium abundance, whereas there's somewhat higher thorium observed elsewhere across SPA. So this tells us that the Spaka material is not highly enriched in incompatible elements. And actually, if you look at the location of Mafic Mound, that's the kind of lowest area of thorium within Spaka. So if that's kind of the more pristine Spaka magma, that's a good case example of that. So this has implications if Spaka is magmatic for the melt source region, the heat source, and the degree of melting. So for instance, Spaka is certainly not a low-degree melt caused by radioactive heating. Instead, it's possible that Spaka is a kind of unique and distinctive type of magma that could possibly be related to the unique geophysical environment within SPA. So Spaka isn't the only interesting thorium-related feature in SPA. I've been working with Ryan Watkins on looking at the thorium hotspots in SPA, and these are up to the northwest. So these are correlated with 2 craters in the northwestern area of SPA. This is Oresme V to the southwest, and Birkelands to the northeast of this figure. So both of these craters are fairly young. They're Upper Imbrian to Eratosthenian. They're both between 60 and 80 kilometers, so they're fairly similar. And they're both associated with these kind of highly localized thorium highs. So Ryan's been looking a lot at the optical properties of these. I wanted to take a look at it from the mineralogy side to see if there's anything mineralogically happening here that could tell us a little bit of why these thorium hotspots are showing up. So first, I looked at this, again, this global scale M-cubed mosaic. We have an update ready to install. Thank you. So I looked at the global scale M-cubed mosaic of band depth. So again, this is showing pyroxene abundance. And so at this scale, there's nothing really remarkable going on here. There's no more or less mafic material in these craters than in anything kind of in the surrounding. So far it looks pretty unremarkable. But I thought maybe I was missing something by only looking at this global mosaic. I wanted to go to individual M-cubed strips to see if there was kind of something hiding in the higher resolution data. So I started by looking at a single M-cubed strip over a RESMI V. Again, this is a map of band depth showing pyroxene abundance. And again, even in this higher resolution data, there's nothing that remarkable about pyroxene abundance across a RESMI V. However, when we look at the absorption band center, this is related to pyroxene composition. There's something really unusual going on in this crater. So you'll see that you have these kind of bright red pixels on the western crater wall. These are indicating a very basaltic type composition. So this is really unusual. We don't see compositions like this in impact crater structures outside of Mare basalts. So you can see that you'll see similar compositions up here in Ingeny and down in these impact craters to the south. Those are Mare basalt patches. So those are places we'd expect to see this basaltic type pyroxene composition. The fact that we're seeing it in a crater wall outside of the Mare is kind of really unusual. So I got to thinking, how could we get a basaltic pyroxene composition in a crater wall? And the first thing I thought about was maybe this is a small basaltic intrusion, perhaps a stalled dike or a sill, something like that, that a RESMI V had tapped, and it had gotten kind of mixed into the local target material, dispersed a little bit so we don't have a pyroxene abundance anomaly. But the pyroxene composition we have here is, it exhibits a very clear basaltic signature. So this is kind of a stretch to say from one M-cubed image. So I needed to go back and look at the eastern side of a RESMI V, as well as Birkeland, to see if this kind of anomaly was showing up in those areas as well, and if it had any chance of explaining these thorium anomalies. So I went back to Envy, I processed a few more M-cubed images, and lo and behold, that's exactly what we saw. So we see this kind of basaltic pyroxene composition showing up in the eastern wall of a RESMI, and then it's even more pronounced up in Birkeland. So it seems like we're kind of onto something here. There's not really a way to get these basaltic pyroxene compositions in the wall of these craters without some kind of basaltic intrusion, kind of shallow, in the shallow surface beneath these craters. We know it's shallow because the central peaks of both these impact craters are both neritic. So similar to what we talked about with Baba, those central peaks are exposing deep-seated neritic material from beneath the kind of material that's been exposed in kind of the walls and rims. And that's where we see this kind of basaltic signature. So I wanted to look at a few more pieces of data to see if these kind of small-scale, creepy basaltic intrusions could be explaining the hotspots. So one thing I looked at was the WAC titanium maps, which were discussed several times earlier today. So in general, where we see titanium enrichments across the lunar surface, these are associated with Mare basalts, so volcanic emplacements. However, and so that's kind of exactly what we see throughout this region. So all of the titanium enhancements we see are mostly associated with Mare basalts. The places where we see them creeping in that aren't associated with Mare basalts are really localized in Birkeland and in a RESMI. So this is kind of another piece of evidence that we have these kind of basaltic compositions that were exposed from beneath the surface by these two craters. So another piece of evidence that these hotspots could be related to creepy, basaltic, shallow, young mafic intrusions. Finally, David Kring asked Ryan earlier about Bouker anomalies that could be associated with some kind of subsurface intrusion. So this is a map of the Bouker gradient. Basically, this is showing areas where you have rapid changes in density. And it's definitely a non-unique map, and I'm not a Grail gravity expert, so I don't want to overinterpret this. But I did want to note that at both craters, we do see an area where there's a high gravity gradient in this Bouker anomaly gradient. So I don't want to overinterpret this, but there could be something here, and it would be great to work with some people who are more familiar with the Grail data to see what their take is on that. Okay, so just to wrap up, when we're looking at the thorium hotspots in SPA, we see that they're associated with Birkeland and Oresme V. These are two relatively young craters, which are both between 60 and 80 kilometers in diameter. The thorium abundance that we see in these hotspots is much lower than some of the near-side creep basalt. So it's something like a third of the abundance. So that's another reason why we think that this could be kind of a dispersed intrusion that was kind of mixed with more kind of local feldspathic material. So it's not a huge monolithic intrusion that stretches between Oresme and Birkeland. It could be a series of dikes or something like that that were then mixed with kind of the local feldspathic materials. And again, that's consistent with the fact that both craters exhibit a weak basaltic signature. So the band depths are fairly weak. There's not a huge abundance of pyroxenes here. But it is consistent with the pyroxenes that are present having a fairly basaltic composition. And again, so those basaltic signatures are confined to the walls, rims, and ejecta of these craters, whereas both of them have more neritic central peaks, which is material exposed from greater depths. And then finally, both craters exhibit a modest titanium enrichment, which is fairly unusual because you don't really see that outside of Mare basalt patches. So our interpretation, very preliminary, but it seems like these observations are consistent with exposure of young, shallow, creepy basaltic intrusions, which have been kind of mixed into and dispersed within more abundant local materials during the crater formations. And that's it. Thank you.
Thanks, Dan. We have time for maybe a quick question. I have one. Based on everything you showed, with SPACA, if you were to send a mission, say Moonrise, to SPA, would you still land in SPACA to get those materials we want for dating the basin, or would you go somewhere else?
So unless you're landing on a central peak like Baba or Finson, I don't think that's a great area if you want to make really sure you're getting basin impact melt. Something like Antoniadi would be great. That seems like the purest area of SPA melt in breccia.
Thanks. All right, so thanks, Dan.